Dr. Cloutis from the University of Winnipeg. So this will be an informal talk today for PISA about one of 4 analog missions that the Canadian Space Agency is actually funding right now. We have one here in Weston, and there's another one at York that we're involved in, and Ed's involved in this one, is targeting Mars methane detection. So it should be interesting, and then of course, everyone should be there at 3:30 for the joint Earth Science, Planetary Science Colloquium, where Ed will be giving us a slightly more formal talk.
Do I have to put on a tie?
On basically the geology and potential biology of Mars. So please come out for that too. And I'll leave more formal introductions of who Ed is and where he came from, how he got to be where he is today for that talk. So,
okay, cool.
take it away, Ed.
All right, thanks. Thanks all for coming out here. What? Yeah, kill. Yeah, that's good. Sure. You guys can't see what you're eating. That might be a good thing. When Oz asked, well, I mean, I'm out here for a bunch of different things, but so I asked Oz if he wanted a topic for the talk. He said he had no idea, so I figured I would talk about the analog mission that we have going on, because probably a lot of you are involved in Oz's analog mission. So we've been exchanging horror stories about the CSA all day, so I will try not to bitch too much about CSA. Oh, I shouldn't have said that. It's going on the web. We can cut that part out. Anyways, I'll talk about sort of the analog mission we have going on, just sort of setting the scene for the science behind it and what it is we're trying to accomplish. So this is sort of an overview of the mission that we're working on, the analog mission. So the idea is to design a realistic rover mission that simulates as closely as possible a Mars rover mission designed to follow the methane to search for life on Mars. And a secondary objective, I guess, is to identify and develop methods to detect life or biosignatures on Mars. So that's sort of the overview. We're doing our simulated mission on the basis of the recent detections of methane in the Mars atmosphere, which may or may not be real. Just again, sort of a little bit of background here. Our knowledge of how methane is produced on Earth, its characteristics, is still incompletely known. And the idea behind running an analog mission on the Earth is that when we eventually send a rover mission to Mars that's designed to search for biosignatures, we'll have some idea, hopefully, of how we should run the mission, what kind of instruments we should equip the rover with, how we should do target selection, and those kind of things. So the idea is to gain some operational experience for an eventual Mars mission that targets methane. So here's sort of some of the tasks that are designed or that are incorporated into the mission. We want to find an Earth-based site with Mars-like conditions as close as possible. So we want to test a rover that will enable characterizing and mapping the target area. We want to test a suite of instruments that could be mounted on a rover. We're going to do field sampling and lab validation so that the data that we get from the rovers, we'll have some confidence that we're seeing real things, that we're getting real numbers. And then identify some geological and biological markers. So we're sort of targeting both the geology and the biology of Mars methane because we think those two are fairly coupled. So there's a technology component to it as well. The idea is for the rover, we want to test mobility. We want to test, as part of this project, we're testing things like autonomous image processing, self-localization and navigation. The communications with the rover will be sort of realistic in terms of limited communication windows between the Earth and Mars. And so we're looking at things like what's the best suite of instruments to put on this rover if we're interested in looking for or determining the source of methane on Mars. So that's just sort of some of the stuff. So the project rationale, the basic thing here is the discovery of methane in the Mars atmosphere has kind of re-energized Mars exploration. And in the talk this afternoon, I'll talk a little bit about how Mars exploration has gone through its ups and downs and the reasons for that. But basically right now, the focus of Mars exploration has really shifted from geological exploration back towards more astrobiology-focused rationale. And so now this sort of the mantra has always been follow the water when we explore Mars. Now it's more follow the methane. So the discovery of methane has kind of, it's really become the driver for future Mars missions at the moment. So there have been detections of methane in the Mars atmosphere from both ground-based and spacecraft-based observations. And what has been found so far is that the methane release appears to be seasonally variable, spatially confined, and associated with hydrated minerals. So here we've got two maps from a study by Mike Muma, where here we're looking at supposed methane concentrations in the atmosphere, red being higher, blues and greens being low, and here's a geological map of the same area. So the areas where we think we see enhanced methane concentrations, here we've got an area of enhanced near-surface hydrogen, and over in these areas we've got hydrated minerals and volatile-rich substrates. So there seems to be, and again I keep sort of qualifying the idea about methane on Mars because it was just a paper that came out in Icarus that made some pretty good arguments that the results they're getting from both the spacecraft and the ground-based observations, they're right on the limits of believability. And so what they think they're seeing on Mars in terms of methane may not be real, but we'll assume for the moment that the observations are reasonably valid. So anyway, so the idea here is that we seem to have this correlation between enhanced methane and hydrated minerals. So that was sort of one of the drivers for our particular analog mission. Just a little bit of background right now. The current data that we have on Mars methane are insufficient to determine whether the methane is biogenic or abiogenic. And our usual way of determining that is by carbon-12, carbon-13 ratios terrestrially, more or less. But the data that we have, the observational data from Mars, is not good enough to determine carbon-12, carbon-13 ratios. So either way, if it's biogenic or abiogenic, it has some important implications for Mars. If it's, because of the atmospheric lifetime of methane is short, sort of decades to a couple of centuries, it implies an active source, regardless of what that source is. If it's biogenic, it implies that there's craters on the surface, right? If it's abiogenic, it implies probably a near-surface heat source. Terrestrially, heat source seems to be required to produce methane in serpentinite type environments. So either way, it's kind of interesting. If the methane is real, if it is in fact being currently produced, it's cool geologically, it's also cool biologically. So it implies that we can learn something about whether Mars has life or whether it's geologically active right now. And so there are ways to determine or to at least constrain the source of the methane, whether it's biogenic or abiogenic. And carbon isotope ratios are sort of the best way to do it right now. The fact that if it appears that the methane is seasonally variable, that would be more consistent with the biological origin. The geology of the areas on Mars where we have enhanced methane doesn't really constrain it one way or the other. But the seasonal variability would be more consistent with a biogenic source than an abiogenic source. Okay. Anyways, so the sort of getting back to our analog mission a little bit, the idea is let's design a rover mission that would simulate as closely as possible how we would go about looking for methane on the Martian surface and also determining or constraining its biogenic or abiogenic origins. Now, because the Mars methane sources are not known, there is no perfect analog site on the Earth. So there's at least two Mars analog missions going on. One is the one we're doing, and the other one is Mike Daly from York University, who's working, I guess, at Axel Heiberg, right?
Yeah.
Yeah, okay. Anywho, so, again, back to sort of this double figure here of enhanced methane and geology. suggests that there's a link to hydrated minerals. So again, the areas of enhanced methane concentration correlate fairly well with non-volcanic, non-basaltic type materials. So hydrated minerals, high concentrations of subsurface hydrogen, and volatile-rich substrates. The 4 Mars Science Laboratory sites are all going to regions of enhanced clays, enhanced phyllosilicates. Terrestrially, the major abiogenic methane production process involves serpentinites, okay, or asbestos. We usually don't use the word asbestos when we talk about what we're doing, right? It's like, ooh, bad word. So we will use serpentinites, just so nobody gets their noses out of joint. So an analog site selection rationale, again, if we want to run a realistic rover mission, let's find a geology, an area of geology that's consistent with some of the areas on Mars that seem to have enhanced methane. Accessible would be good. And also we want a site that will allow us to test not only our science instruments, but the rover technology itself. So the site selection criteria, my God, that's a busy slide. Okay, anyways, the site selection criteria, we're looking at it from the science team perspective in terms of the right kind of mineralogy. We want sort of a range of microenvironments. We want a site where we can test our instruments under realistic conditions. We also, because there's a technology component to it, we want a site that will satisfy the rover constraints that we have. So, in other words, can't be greater than 30-degree slope, vegetation free, not too rubbly, all that kind of stuff. So again, back to the whole serpentinite thing. Here is a map from Bethany Ellman's study. This is in one of the regions of enhanced methane concentration. And this particular mineral map shows where we have a couple of sort of key minerals. One is serpentine occurrences, which are shown by a couple of red dots here. And the other one is magnesium carbonates, which are a weathering product of serpentinites. And so in a couple of spots we have close association between the occurrence of serpentine and the occurrence of magnesium carbonates. So we've kind of used that linkage as one of the criteria for selecting a site. So when serpentinites weather, generally one of the weathering products is magnesium carbonates, and through the chemical reaction process, you can provide hydrogen, which can then be converted to methane. And so we've done, we did some preliminary work on some of the asbestos deposits in Quebec, and these are some of the spectra that have been acquired from the Omega instrument on Mars, and they match very well the signatures of the serpentines in Quebec. So we've got a good first order match between the geology of the serpentinite deposits in Quebec and the geology of some of these serpentinite bearing areas on Mars. So anyways, based on this idea that let's take a look for serpentinite rich areas, terrestrially, we pretty much quickly converged on some of the serpentinite or asbestos deposits in Quebec, in the, coincidentally, the asbestos region of Quebec, right? And the deposits have the right geology and the right spectral properties. So this is sort of an example of, you've got serpentine here, and through weathering process, you form various types of carbonates. That involves the release of hydrogen, carbon dioxide, rich groundwater, heat, you get the right reaction, and you can produce methane. So these are, again, the spectra of some of the samples from Quebec, and we can easily identify the difference between magnesium carbonate, serpentinite, and some of the iron oxides that also form during the weathering process. So spectrally, we have all sort of the right stuff. So for analog site selection, there's a lot of asbestos mines through Quebec. And we did our initial site visit to pick the analog sites in June of last year. And we had a bunch of people along, including various and sundry students. See, I don't ignore the little people in my presentations, right? And so when we looked at a bunch of both active and retired asbestos mines, we started sort of characterizing them or ranking them in terms of desirability. So we ended up with sort of a tier 1 suite of sites and a tier 2 suite of sites. So the tier 1 sites that we looked at, that we visited about 30 or 40 locations in Quebec. The tier 1 sites are the asbestos mine right by the town of Asbestos, big open pit mine. The Nordbestos mine over here is about 10 kilometers from Asbestos. It's an abandoned asbestos mine. And the East Broughton Quarry is in the same area, and it is, it's more of a talc serpentinite mix. But again, they're good from the perspective of the right geology, accessibility, rock types, fracturing, sort of a whole host of criteria that we use to rank the sites. So here's the Jeffrey mine in the town of Asbestos, and just a couple of sort of views of the mine. Easily accessible. The mine owners are happy to host us, so it's all good. Access roads all around the mine, so accessibility is good. The size of the site is good, because one of the CSA requirements was 500-meter traverses by a rover. So the mine site itself is sort of a few kilometers across, so we easily meet that criteria. We can get our instruments into here, so it met all our requirements for a good site. There's faulting that's present in the mine site, which is good, and fissures, so that if methane is being produced in the subsurface, these are the kinds of targets that we would focus our rover explorations on. Look for fractures, major faults, major fractures in the ground, and see if there is in fact enhanced methane production at these places where you have some access to the subsurface. Just a couple more views here. Here's the Serpentine itself. Again, it's a very, the deposit is quite highly fractured. So our exploration of the site will be based largely on detecting and taking the rover to major fractures, major faults within the deposit. And we're also going to look to see whether there are changes in the geology at the site in terms of proximity to fracture. So in other words, does the process of methane production lead to changes in the geology as you move away from major fractures and faults? That we don't know yet. And so within the mine site during our visit, we've also looked at potential rover starting positions, because again, one of the requirements is that we test rover technologies. It's not just about detecting methane, but also seeing how a rover performs under reasonably realistic conditions. So we identified a number of locations within the mine site where we could deploy the rover from. And the rover traverses aren't shown here, but most of the faulting within the mine site kind of runs northeast, southwest, and you can see here there's a big change in color. It's a major fracture system there. And so we've identified a couple of places in the mine where we can run our rovers within the mine site. So again, in terms of sort of ranking the sites in terms of desirability, the tier 1 sites met our criteria for appropriate geology. Variety of terrains for rover tests, from intact bedrock to fine-grained materials, and just those little things about accessibility, logistics, all that kind of stuff. The tier 2 sites, these were largely tailings piles. So they have the right geology. It's all the waste rock from the mining process, a more limited variety of terrains, and they are highly accessible. And here's a couple of my students playing when they should be working. Okay. Some of you have met these guys. This is Genevieve, that's Paul. So just in terms of if we can't access our tier 1 sites, we can do most of our objectives. We can meet most of our objectives at these tailings pile sites. Okay, so in terms of sort of how we're going to tackle the mission. We're going to search for various indicators of methane production. So we're going to look at geological factors, and we're going to look at biological factors. So it's not just a geology mapping mission. We're also going to look at gas composition, and we're going to do microbiome kind of things. Okay. Clearly that indicates I'm not a microbiome kind of guy when I say that. Okay. So here's sort of a kind of the suite of instruments that we're planning to deploy in the mission. We have a tunable laser, which we will look for methane absorption lines, and the resolution is high enough that we can distinguish between carbon-12 and carbon-13 methane. A UV-vis infrared spectrometer for site geology and navigation, so that we can target the appropriate rock types. So in other words, magnesium carbonates, serpentinites. We're going to look at UV fluorescence for biomolecule detection, and there's a requirement that we demonstrate a capability to collect samples, rock samples. We're also going to, in addition to what's going to be mounted on the rover, we're going to bring in a Raman spectrometer, and we're going to test out some geophysical techniques as well, just to see if these techniques are complementary or if they add anything to our investigation. Okay? We're thinking, for instance, that certain geophysical techniques might be good for determining that third dimension of the site. So in other words, is there an extensive system of fractures that may provide pathways for methane to the atmosphere? So major project tasks, site selection visits were done. We picked our site. All the gory planning is in progress. Our first deployment of the rover will be in the summer this year, in June. Second deployment for May, June-ish of next year. And we'll also do some winter field visits to look mostly for seasonal variations in methane production, to see if that's in fact the case. There's a science team, cast of thousands. Oh my God, I'm done. Oh, wow, that was quick. Okay, that's it. Questions, comments?
So we have lots of time.
Yes, we do.
Interrogating.
Questions are always better than presentations. Matt?
About the tunable laser
Yeah.
for the methane and isotopes, what kind of sensitivity do you have down to the parts per billion that are supposed to be there at Mars?
That's a good question. Yeah, I think so. I think we can do PPD. Yeah.
And is it a chamber that emits some atmosphere and then shoots the laser through with a long path length?
No, it's just going to be straight reflectance. Yeah. So we're gonna look at, we'll look at a rock face, but there's an intervening atmospheric path length, right? So we're just going to work at. I'm trying to remember what the resolution is. How many picometers? I can't remember. 3 picometer maybe resolution. So we can pick out C12 lines and C13 lines. Yeah.
Just one more thing about it then. Do you think there's any chance you could see the doubly substituted C13?
I'm kind of thinking we can, but we're more focused on the C12, C13. Yeah. You're thinking like deuterium hydrogen, right?
Yeah, because maybe that's an even better biosignature with multiple substitution.
I have kind of brought that up, but then they just ignore me and move on. So yeah, I don't know why. But no, I've thought about that. I mean, you can look at, doubly, singly substituted, doubly, triply substituted even. There's a whole, and quadruply, right? There's all kinds of ranges. But I think the main thing is going to be the C12, C13. You should have lines from, I don't know if that stuff is in high tran though.
Actually, it isn't. That's one of the issues with the Mars detections from the ground.
Okay.
The doubly substituted isotopologue of methane in our atmosphere isn't in the ITRAN database, so you could actually be seeing it on Mars through the atmosphere, except what you're seeing is a problem with the ITRAN.
Yeah, yeah, I know the high trend thing is limited, but you're right. That's something I've thought about, but I don't know that much work has even been done terrestrially on the significance of deuterium hydrogen substitutions in methane and what the bio versus abiogenic implications. Yeah. Thesis project.
Yes.
You just add that to your plate of things to do, right? You got time.
Shout out.
Yes, and I'm wondering, I've heard that obviously methane is an important gas to look for if you're looking for a possible life. But are there other sort of trace gases that you might consider looking for besides methane?
Yes. For this particular mission, we're only going to focus on methane. But in the talk this afternoon, I'm going to talk about another mission that we've got going on, which is a Mars Trace Gas Orbiter, and that will have, it will cover the infrared, and so they're going to, it's going to run from like 2 to 16 microns at sub nanometer resolution. So they are going to look for other trace gases as well. Yeah, things that may be more characteristic of biogenic versus abiogenic. Yeah. So, but for this particular one, we're really just going to do the methane at this point. Yeah, but there is a lot of thought about other trace gases for sure. Yeah. The problem is that you're going to be down in parts per trillion for a lot of these, so detectability is going to be an issue. At least with methane, we're talking sort of to the range that I've seen is like 10 to 100 parts per billion. So, yeah, much more detectable than other gases that might be present, but there will be a capability to cover their absorption features. Whether we find them or not is another story, but at least the capability will be there. Yeah.
Do we have the ability to detect methane on Earth the way that they detect it on Mars?
Yeah.
Do we have a comparable site on Earth that we can detect from space that shows methane production? Because the follow-up is that if you're seeing seasonality in what goes on Mars, what's the temperature? What's the temperature there for those places?
Yeah. No, it's about as cool as it is today here on a summer day on Mars. The problem, yeah, one of the issues, or one of the things about the Mars methane is that the atmosphere mixes fairly rapidly on Mars. And so the fact that you're seeing enhanced methane concentrations in certain parts on Mars implies a very active source, because the mixing time is like on the order of a decade, I think. And so if you had methane emissions on Mars, after 10 years, and let's say it stopped, after 10 years, you wouldn't see these enhanced concentrations on certain parts of the surface. The atmosphere would have mixed thoroughly within a decade. So they're talking about an active, as in truly an active source of methane production. I just read this article that is coming out in Icarus about the reality of the methane detections, and it's tough to detect methane in the Mars atmosphere, regardless of anything. And so the question then is, one of the things that people say is that, well, there's got to be methane because it's been detected by both orbiting spacecraft and Earth-based telescopes. Okay, they work with different technologies, and the paper that's in Icarus raised some serious questions about the technology that they're using, because you're right on the edge of detectability. And so it could be that one of the issues was that maybe they're not correcting for, in the Earth-based observations, they're not correcting for some trace gas, and I can't remember what it is now. For the orbiting spacecraft data, you're looking for a slight bump on the side of a big absorption feature. So the data is, like I said, it's right on the edge of believability, unfortunately. Yeah.
So do we have anything on Earth, like we produce a bunch of methane from source and detect it from space?
Yeah. There's already a couple of orbiting terrestrial spacecraft that map methane detection or methane concentrations in the atmosphere. Yeah, so that's.
But can they link them back to a source?
I've never seen them try to do that. Yeah. Usually they're looking at.
You want to see it over a volcano?
Should be.
I mean, Dave Lubinsky, I mean, didn't he measure methane and when he pointed spectrometers over the volcanoes?
With over New Zealand.
Yeah, they use that.
You certainly see it over fires,
Yeah, you can get it with ground-based spectrometers that you point through volcanic plumes. Yeah, then you can pick it up. But space-based, I don't know.
Yeah, I'm not really, because then you'd have an idea of what you could be seeing on ground that would be analogous to the methane source to what you could detect from space.
Yeah, well, there's a whole.
Moppet measured. Doesn't Moppet get methane as well?
I think so. Yeah.
Or at least they were supposed to, and everything. So I mean, yeah, you can see it. People see it from space all the time.
Yeah, terrestrially, sure. And then the problem, or what they do on Mars is you have to, and they've done this, you account for the Doppler shift too, right? Mars is either moving towards you or away from you, so that shifts the lines, which helps in some ways, but sort of hurts in other ways. So they've taken into account, a lot of the complicating factors, I think, but there's so many emission lines in the atmosphere. We know the main ones, but there's a lot of other trace gases that could create these interferences. Yeah, so it's a tough observation to do.
The seasonality part, you think the seasonal variation, you would link that to islands.
That's right. Yeah. The seasonal variations have really only been seen in the terrestrial observations. So you could argue that maybe there's a seasonal variation in whatever terrestrial gas there is that you're looking through with your telescope, right? The orbital data around Mars from the Mars Express are sort of a couple of observations here and there. So they haven't detected a seasonality, but it's only because they haven't done enough observations. And the signal to noise is so crappy that they have to average thousands of spectra to even see something. So the seasonality is based largely on terrestrial observations from Mauna Kea, from a few other places. So you've got all the terrestrial atmosphere effects to deal with. And
so maybe summer, like warm more, cold less.
Yeah.
There's a special issue on Mars methane out this week, I think, in Planetary Space Science.
Yep.
I glanced at one of them that's talking about, we're now seeing more methane over board caps. Talking about
That's right.
again.
Yeah.
The distribution seems totally different to figure out here.
Yeah.
So it does raise some kind of suspicions about
Yeah,
how we actually look at it.
Yeah, the PSS papers are all, sort of more of the same. The lone voice in the wilderness it's just coming out of Icarus right now, and it's actually I liked it. It was pretty, oh my God, maybe they haven't done the corrections that they should be doing to the data.
So we're not seeing anything.
Maybe not, yeah.
Since we have expert astrobiologists here, what would be the consensus, would you say, maybe not your own opinion, your colleagues and everything? You're kind of hanging a lot here on assuming that if there is life anywhere else, it's going to be played by all the same rules and everything. Right? If it's life like on Earth, then it's going to do methane like this. If it's life on Mars, is it all bets off, or is the consensus of your community, you use that assumption that it's going to be Earth-like, and no one really argues that, and that's a completely spurious thing to even bring up. What would be how would you answer that?
We argue the fact that it's got to be based on thermodynamics, and thermodynamics isn't just a good idea.
Yeah.
So any life form has to require energy, so it's based on that.
So any life form has to have a methane output at some point.
So what reactions can you write where you have a negative delta G? And if you do, then life could catalyze that kind of reaction.
Okay, thanks.
You get methanogens at pH 10 because one is it chrysotile or amphibole?
It's chrysotile.
Okay, so you're fine. But you have methanogens growing at pH 10. The pore waters and those kinds of things are pH 10 to 11. And I don't know when you get methanogenesis at pH 10 or 11.
Yeah, one of the things we're going to see is where and how is methane being produced at the asbestos mine. When we did our site visit, methane is not something we like to talk about at the mine site. You're already getting enough bad press with asbestos, right? You added methane, then they're just toast. So they don't like to talk about the methane, but yeah, there is methane produced at the site. So one thing we're going to look at is the relationship between where is the methane at the mine site and does it relate to structure, mineralogy, structures. That's what we're going to look at.
Sorry. So, I guess I have kind of two questions, because is the methane produced at the mine site, is it biogenic or abiogenic?
Don't know.
Because with the seasonality, everyone seems to think, oh, seasonality, clearly that's biota. But should there not be also clearly abiotic geochemical processes that would also be heat temperature dependent?
Yeah. Yep.
So,
Yeah, I mean, the general assumption is that methane production in these kind of geological environments, you need 300-400 degrees C to make it, but there's also a lot of evidence that you can produce methane at ambient temperatures too. It's not as much, it's obviously a more efficient process when you got a nice heat source, but yeah, you can certainly produce it under ambient conditions. So then if that's the case, then yeah, you would expect a seasonality as well, just with ground temperatures, if it's a near surface process and it's geological. Yeah. So I think it's going to come down to the isotopes. It's going to be what nails it. Miss?
It says on one of your instruments is a UV fluorescence.
Yeah.
So are you looking for microbes as well?
Yeah.
To try and prove that methane's linked
Yeah.
to them or not? Or?
Yeah, because we're going to have like a CMOS cameras on the rover anyways, so the thought is we'll just throw a UV light source on there of some sort and see if we get fluorescence. So it's just kind of a test instrument.
Okay.
Yeah, we'll probably get something. Yeah, it's just it's not the main focus, but it's just, why not? We can do it. Yeah. Michael?
The seasonality thing, they seem to kind of be forgetting about how much of the atmosphere is moving around from summer to winter. Fully half the atmosphere freezes out on the poles and then it blows back and you get one hell of a wind going
Yeah.
the equator poleward and then the other direction
Sure.
again. So
Yeah.
wouldn't that essentially create a seasonal change in that methane source even if it was running constantly?
Yeah, I don't know if these...
It takes a long time to mix it thoroughly through the atmosphere, but there's a hell of a wind blowing
Yeah.
back and forth.
Yeah, I don't know if these like enhanced concentrations here correlate with wind direction. I don't know. Yeah, it might, but I kind of doubt it. I think these are sort of Mars summer observations. Yeah, yeah, but yeah, the number that I've seen is like, okay, in a decade you're going to thoroughly mix whatever methane is there.
But in the wintertime, since all your atmosphere is going to the poles, it's just blowing it out.
Yeah.
It's just blown all northward. It's not really a seasonal thing anymore. In the initial paper, it's just entirely.
Yeah. Oh yeah. There's a lot to take about the papers. Yeah.
What biomolecules are you trying to detect?
I have no idea. That's why I turned you. I don't know. We're just gonna try UV fluorescence. Lyle, White, and Miguel, they're gonna look after that whole bio side of things. Yeah. We'll grab some samples, grow some stuff, see what's there.
Tentative things have, a whole slew of fluorescent enzymes or cofactors. Red 420 lights up.
Yeah.
With all the people purifying it with throw UV bombs and things like that on the side of the column so we can track it.
Yeah.
But there's no reason to believe it would come anywhere near the surface.
That's right. Yeah.
Because they're anaerobes. So,
Yeah.
you can do it in culture and it'll work,
Yeah.
but...
The UV fluorescence is just more of a technology demonstrator than anything else. Yeah, but Lyle and those guys they're definitely going to get subsurface samples and work their magic on the bugs. Yeah.
Yeah, well, I guess it'll grow and work, but your rover's never going to find it in line.
Yeah. One of the reasons that we did pick the mine is because it's still an active mine site, and so anaerobes aren't going to be near the surface, but if there's active mining going on, then you're constantly exposing new material. So the thought is that, we'll do some sampling at sort of the newly exposed areas in the mine site, and that way we don't have to drill really deep down. Although they are starting to sink a shaft too, so we can get samples that way as well. The plan is to go underground now at the mine site
Just wondering how many seeps you've got. So if you look at the mine slides in South Africa, we can find methanogens, we can find metallotropes that produce nice pigments,
Yeah.
light efforts for numbers. So a mine slime would make a good sample, or a
Yeah.
seep as a transport mechanism.
Oh, okay.
To bring something to the surface.
Yeah.
Could work, but fractures, well, I guess the fractures is if they're flowing, then they might be good candidates, but the
Yeah.
stuff that's dry is.
Yeah. There's ground, I mean, they have to dewater the mine, so there's definitely that going on. So yeah, there's a lot of places that we can sample things. Yeah. But, you know, unfortunately, sort of the main thing is stupid Rover, right? Has to do all that kind of stuff. So we're not getting a chance to do a whole lot of interesting science, but we're kind of, under the radar a little bit. Yeah, we do some stuff. Yeah.
Trouble with dewatering, we saw at Morenci that you could find aerobic organisms down to 500 meters.
Oh, yeah.
And acid environments not even there, so it creates a whole datahouse, which isn't what we want.
Yeah.
Last question.
Just thinking about carbon reservoirs and isotopic compositions of the different reservoirs. So let's say it all works and you get a Martian methane delta 13C.
Yeah.
Okay. Then what reservoir was that fractionated from? Like, is that going to be something that the rover will attempt to measure? Or are we going to constrain that with meteorites and models of the mantle, or what?
No idea. Yeah.
Like,
I mean,
to
you know,
prove
yeah,
it's a
so let's say you
byproduct.
see, see some big isotopic fractionation, you still sort of need to know what your initial reservoir values were. Yeah.
I mean, there's an idea that the whole Martian mantle is depleted in C13.
Yeah.
So you might already get more negative values that would scream biology on Earth, but maybe are not
Yeah.
big fractionation of that.
You could use the carbonates that you've got in like Allen Hills, right, as sort of one data point. See what kind of fractionation you have in the carbonate steps in that thing.
Methane bicarbonate with fairly large fractionation, I think.
Yeah. Yeah. Yeah, the initial carbon ratio is just one of those, we don't talk about it, so.
Never mind. I know nothing.
All right. Thanks again, Ed.
Okay.